The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, let's start. So last lecture we were talking about elasticity as an example of a field theory, statistical field theory. And I ended the class by not giving a very good answer to a correct question that was asked. So let's go back and revisit it. So the idea that we had was that maybe we have some kind of a lattice. And we make a distortion through a set of vectors in however many dimensional space we are. And in the continuum format, we basically regarded this U as being an average over some neighborhood. But before going to do that, we said that the energy cost of a distortion at the quadratic level, of course we can expand to go to higher level, was a sum over all pairs of positions, all pairs of components, alpha and beta running from 1 to however the dimensionality of space is, U alpha at R, U beta at R prime, the components alpha beta of this vector U at these two different locations, let's say R and R prime here. And then there was some kind of an object that correlated the changes here and here, may be obtained as a second derivative of a potential energy as a function of the entirety of the coordinates. And this, in principle, for a general function of all of these distortions, depends on all pairs of variables. But then we said that because we are dealing with a lattice, and one pair of coordinates in the lattice is the same as any other pair of coordinates that have the same spatial orientations, that this function really is a function of the separation R minus R prime, which of course can be a vector on this lattice. And the fact that it has this form then allows us to simplify this quadratic form rather than being a sum over pairs n squared, if you like, into a sum over one coordinate, which is the wave vector obtained by Fourier transform. So once we Fourier transform, that sum delta V can be written as a sum over just one set of k vectors, of course, appropriately discretized depending on the overall size of the system and confined to a Brillouin zone that is determined by the type of wavelengths that the lattice structure allows. And then this becomes U alpha tilde, the Fourier transform, evaluated at k, and the other point, which is minus k, that if I write it again as k, is really this. And this entity, once we Fourier transform it, becomes a function of the wave number k. Now, there is one statement that is correct, which is that if I were to take the whole lattice and move it, then essentially there will be no cost. And moving the entire lattice only changes the Fourier component that corresponds to k equals to 0, translation of everything. So we know for sure that this k alpha beta at k equals to 0 has to be 0. Okay? Now we did a little bit more than that then. We said let's look not only at k equals to 0, but for small k. And then for small k, we are allowed to make an expansion of this. And this is the expansion k squared, k to the fourth, etc., that we hope to terminate at low values of k. Now that itself is an assumption. That's part of the locality that I stated, that I can make an expansion as a function of k. After all, let's say k to the 1/2 is a function that goes to 0 at k equals to 0, but it is non-analytic. Turns out that in order to generate that kind of non-analyticity in this function in real space as a function of separation should decay very slowly. Sometimes something like a Coulomb interaction that is very long range will give you that kind of singularity, but things that are really just interacting within some neighborhood, or even if they are long range, if the interaction falls off sufficiently rapidly, and that's one of the things that we will discuss later on, precisely what kind of potential allow you to make an expansion that is analytical in powers of k and hence consistent with this idea of locality. Let's also ignore cases where you don't have inversion symmetry, so we don't need to start and worry about anything that is linear in k. So then the first thing that can appear is quadratic in k. Okay. Now when we have things that are quadratic in k, I have to make an object that has two indices, alpha and beta. And, well, how can I do that? Well, the kinds of things that I mentioned last time, we could have a term that is k squared, and then we have a delta alpha beta. If I insert that over here, what do I get? I will get k squared delta alpha beta will give me u tilde squared. So that's the term that is in an isotropic solid identified with the shear modulus. Again, if the system is isotropic, I don't know any distance apart from any other distance, any direction, any other direction, I can still make another tensor with two indices alpha and beta by multiplying k alpha k beta. If I then multiply this with this, I will get k dot u, the dot product, squared. So that's the other term that in an isotropic solid was identified with mu plus lambda over 2. Now, as long as any direction for k in this lattice is the same, those are really the only terms that you can write down. But suppose that your system was anisotropic, such as, for example, a rectangular lattice. So let's imagine that we put a whole bunch of points here to emphasize that rather than something like a square lattice, we have something that is very rectangular. Okay? In this case, you can see that the x and y directions are not the same. And there is no reason why this k squared here could not have been separately kx squared plus some other number ky squared. And hence, the type of elasticity that you would have would no longer depend on just two numbers, what, say, over here with 3. In fact, there will be more. And precisely how many independent elastic constants are given depend on the point group symmetry, the way that your lattice is structured over here. But that's another story that I don't want to get into. But last time I was rather careless, and I said that just rotational symmetry will give you this k squared, k alpha, k beta. I have to be more precise about that. And so this is what's happening. Now, given that you have an isotropic material, then the conclusion is that the potential energy will have two types of terms. There is the type of term that goes with k squared u tilde squared. And then there's the type of term that goes with mu plus lambda over 2 k times u tilde squared. Now you can see that immediately there is a distinction between two types of distortion. That is, if I select my wave vector k here, any distortion that is orthogonal to that then will not get a contribution from this. And so the cost of those so-called transverse distortions only come from U. Whereas if I make a distortion that is along K, it will get contribution from both of those two terms, and hence the cost of those longitudinal distortions would be different. So when we go back to our story of how does the frequency depend on a whole bunch of k's, we can see that when we go to the small k limit, in an isotropic material, we've immediately established that there will be one longitudinal mode, and we'll have some kind of longitudinal sound velocity. And in 3 dimensions, there will be 2 branches of the transverse mode that fall on top of each other. As I said, once you go to further larger k, then you can include all kinds of other things. In fact, the types of terms that you can include at 4th order, 6th order, etc., again are constrained somewhat by the symmetry, but their number proliferates, and eventually you will get all kinds of things that could potentially describe how these modes depend. And those things are dependent on your potential. I don't know too much about. And why was this relevant to what we were discussing? We said that basically once you go to some temperature other than 0, you start putting energy into the modes. And how far in frequency you can go given your temperature, typically the maximum frequency at a particular temperature is of the order of kT over h bar. So that if you are at very high temperatures, all of the harmonic oscillators and all of the vibrations are relevant. But if you go to low temperatures, eventually you hit the regime where only these long wavelength, low frequency modes are excited. And your heat capacity was really proportional to how many modes are excited. And from here you can see, since omega goes like t, either the k for longitudinal or the k for transverse has to be proportional to t, the maximum one. Larger values of k would correspond to frequencies that are not excited. So all of the modes that are down here are going to be excited. How many of them are there? Up to from 0 to this k max, that is of the order of kT over h bar and some sound velocity. So you would say that the heat capacity, which is proportional to the number of oscillators that you can have, you have kT, kB per oscillator. The number of oscillators is roughly volume times kT h bar v cubed if you are in 3 dimensions. We saw that it was 1 in 1 dimension, so in general it will be something like d. Of course, here I was kind of not very precise because I really have to separate out the contribution of longitudinal modes and transverse modes, etc. So ultimately, the amplitude that I have will depend on a whole bunch of things. But the functional form is this universal t to the d. So the lesson that we would like to get from this simple, well-known example is that sometimes you get results that are independent in form for very different materials. I will use the term universality. And the origin of that universality is because you are dealing with phenomena that involve collective behavior. As k becomes small, you are dealing with large wavelengths encompassing the collective motion of lots of things that are vibrating together. And so this kind of statistical averaging over lots of things that are collectively working together allows a lot of the details to, in some sense, be washed out and gives you a universal form, just like adding random variables will give you a Gaussian if you add sufficiently many of them together. It's that kind of phenomenon. Typically, we will be dealing with these kinds of relationship between quantities that have dimensions. Heat capacity has dimensions, temperature has dimensions. So the amplitude will have to have things that have dimensions that come from the material that you are dealing with. So the thing that is universal is typically the exponents that appear in these functional forms. So those are the kinds of things that we would like to capture in different contexts. Okay? Now, as I said, this was supposed to be just an illustration of the typical approach. The phenomenon that we will be grappling with for a large part of this course has to do with phase transitions. And again, this is a manifest result of having interactions among degrees of freedom that causes them to collectively behave separately, differently from how a single individual would behave. And the example that we discussed in the previous course and is familiar is, of course, that of ice, water, steam. So here we can look at things from two different perspectives. One perspective, let's say we start by, actually let's start with the perspective in which I show you pressure and temperature. And as a function of pressure and temperature, low temperatures and high pressures would correspond to having some kind of a actually, let me not incur the wrath of people who know the slopes of these curves precisely. So there is, at low temperatures, you have ice. And then the more interesting part is that you have, at high temperatures and low pressures, gas. And at intermediate values, you have, of course, the liquid. And the other perspective to look at this is to look at isotherms of the system for pressure versus velocity. So basically, what I'm doing is I'm staking at some temperature and calculating the behavior along that isotherm of how pressure and volume of the system are related. So when you are far out to the right, you have behavior that is reminiscent of an ideal gas. You have PV being proportional to the number of particles and temperature. As you lower the temperatures and you hit this critical isotherm at Tc, the shape of the curve gets modified to something like this. And if you are looking at things at isotherms that are even lower temperature, you encounter a discontinuity, and that discontinuity is manifested in a coexistent interval between the liquid and gas. So isotherms for T less than Tc have this characteristic form. Okay. So here I have not bothered to go all the way down to the case of the solid, because our focus is going to be mostly as to what happens at this critical point, Pc and Tc. where the distinction between liquid and gas disappears. So there is here the first case of a transition between different types of material that is manifested here, the solid line indicating a discontinuity in various thermodynamic properties. Discontinuity here being, say, the density as a function of pressure. Rather than having a nice curve, you have a discontinuity. And these curves, isotherms, are suddenly discontinuous. And the question that we posed last time, last semester, was that essentially all the properties of this system, the thermodynamic properties, I should be able to obtain through the partition function, log of the partition function, which involves an integral, let's say, over all of the coordinates and momenta of some kind of energy. And this energy, I mean, the part about momenta is not particularly important. You could just get rid of that. And the part about the coordinates involves some kind of potential interaction between pairs of particles that is not that difficult. Maybe particles are slightly attracted to each other when they are close enough and they have a hard core. But somehow, after I do this calculation, bunch of integrals, all of them are perfectly well behaved. There is no divergence as the range of integration goes to 0 or infinity. I get this discontinuity. And the question of how that appears is something that clearly is a consequence of interactions. If we didn't have the interactions, we would have ideal gas behavior. And maybe this place is really a better place to go and try to figure out what's going on than any other place in this phase diagram. And the reason for that is in the vicinity of this point, we can see that the difference between liquid and gas is gradually disappearing. And so in some sense, we have a small parameter. There's some small difference that appears here. And so maybe the idea that we can start with some phase that we understand fully and then perturb it and see how a singularity appears is a good idea. I will justify for you why that's the case and maybe why we can even construct a statistical field theory here. But the reason it is also interesting is that there is a lot of experimental evidence as to why you should be doing this. We discussed the phase diagrams, and we noticed that an interesting feature of these phase diagrams is that below Tc, when the liquid and gas first manifest themselves as different phases, there is a coexistence interval. And this coexistence interval is bounded on the two sides by the gas and liquid volumes or alternatively densities. Now, the interesting experimental fact is that when you go and observe the shape of this curve, for a whole bunch of different gases, here you have neon, argon, krypton, xenon, oxygen, carbon dioxide, methane, things that are very different, and scale them appropriately so that all of the vertical axes comes to 1, so you divide P by PC. You appropriately normalize the horizontal axis so the maximum is at 1. You see that all of the curves you get from very, very different systems, after you just do this simple scaling, fall right on top of each other. Okay? Now, clearly, something like carbon dioxide and neon, they have very different interatomic potentials that I have to put in this calculation. Yet, despite that, there has emerged some kind of a universal law. And so I should be able to describe that. Why is that happening? Okay? Now, I'll try to convince you that what I need to do is similar to what I did there. I need to construct a statistical field theory. But we said that statistical field theories rely on averaging over many things. So why is that justified in this context? So there is a phenomenon called critical opalescence. Let's look at it here. Also, this serves to show something that people sometimes don't believe, which is that since our experience comes from low pressures where we cool a gas and it goes through a liquid, or heat it and liquid goes to a gas, and you know that these are different things, it's kind of, they find it hard to believe that if I repeat the same thing at high pressure, there is no difference between liquid and gas. They are really the same thing. And so this is an experiment that is done going more or less around here where the critical point is. And you start initially at the low temperature side, where you can see that at the bottom of your vial you have a liquid, and a meniscus separates it nicely from a gas. As you heat it up, you approach the critical temperature, well, the liquid expands and keeps going up. And once you hit TC and beyond, well, which one is the liquid and which one's the gas? You can't tell the difference anymore, right? There is a variation in density because of gravity. There is more density down here than up there. Okay, now what happens when we start to cool this? What happened? That's called critical opalescence. You can't see through that. And why? Because there are all of these fluctuations that you can now see. Right at TC, when the thing became black, there were so many fluctuations covering so many different length scales that light could not get through. But now gradually the size of the fluctuations, which exist both in the liquid and in the gas, are becoming small, but still quite visible. So clearly, despite the fact that whatever atoms and molecules you have over here have very short range interactions, somehow in the vicinity of this point, they decided to move together and have these collective fluctuations, right? So that's why we should be able to do a statistical field theory, and that's why there is a hope that once we have done that, because the important fluctuations are covering so many large numbers of atoms or molecules, we should be able to explain what's going on over here. Okay, so that's the task that we set ourselves. Anything about this before I close the video? Okay. Yes?
There are gases that don't, when rescaled, their plots don't comply to that?
No. In the vicinity. So maybe the range of the things that can be collapsed on top of each other is small. Maybe it is somehow so small that you have to really do things at very low pressure differences in order to see that. But as far as we know, if you have sufficiently high resolution, everything will collapse on top of that curve. And what is more interesting than that it is not even confined to gases. That is, if I had done an experiment that involved mixing some protein that has a dense phase and a dilute phase, and I went to the point where there is a separation between dense and dilute, and I plotted that, that would also fall exactly on top of this curve. So it's not even gases, it's everything. And so okay. So yes?
Can there be built a system where some kind of the same phenomenon is observed in not 3 dimensions?
Yes, and we will discuss those too.
And the exponents will change?
Yes.
So it's at least dimension dependent.
Well, you may anticipate from that t to the d over there that dimension is an important quantity. Yes. Okay? Anything else? All right. I'm going to, rather than construct this theory, this statistical field theory for the case of this liquid gas system, I'm going to do it for the case of a ferromagnet, just to emphasize this fact that this result, this set of results, spans much more than simple liquid gas phenomena, a lot of different things. And secondly, because writing it for the case of ferromagnet is much simpler because of the inherent symmetries that I will describe to you shortly. So what is the phenomena that I would like to describe? What's the phase transition in the case of a ferromagnet, like a piece of iron? Well, one axis that is always of interest to us is temperature. And if I have a piece of iron or nickel or some other material, out here at high temperatures, it is a paramagnet. And there is a critical temperature Tc, below which it becomes a ferromagnet. Which means that it has some permanent magnetization. And actually, the reason I drew a second axis is that a very nice way to examine the discontinuities is to put an external magnetic field and see what happens. Because if you put an external magnetic field, like you put your piece of magnet enclosed in some current carrying loop, so that you have field in one direction or the other direction, then as you change the strength of the field on the high temperature side, what you find is that if I plot where the magnetization is pointing, well, if you put a magnetic field on top of a paramagnet, it also magnetizes. It does point in the direction of the field. The amount of magnetization that you have in the system when you are on the high temperature side looks something like this. At very high fields, all of your spins are aligned with the field. As you lower the field, because of entropy and thermal fluctuations, they start to move around. They have too much fluctuation when you are in the phase that is a paramagnet. And then when the field goes through zero, the magnetization reverses itself, and you will get a structure such as this. So this is the behavior of magnetization as a function of the field if you go along a path such as this, which corresponds to the paramagnet. Now, what happens if I do the same thing, but I go along a looped route such as here? Okay? So again, when you are out here at high magnetic field, not much happens. But when you hit zero, then you have a piece of magnet. It has some magnetization. So basically, it goes to some particular value. There is hysteresis. So let's imagine that you start with the system down here and then reduce the magnetic field. Then you would be doing a curve such as this. So in some sense, right at h equals to 0, when you are for t less than tc, there is a discontinuity. You don't know whether you are one side or the other side. And in fact, these curves are really the same as the isotherms that we had for the liquid gas system if I were to turn them around by 90 degrees. The paramagnetic curve looks very much topologically like what we have for the isotherm at high temperatures, where the discontinuity that we have for the magnetization of the ferromagnet looks like the isotherm that we would have at low temperatures. And indeed, separating these two, there will be some kind of a critical isotherm. So if I were to go exactly down here at Tc, what I would get is a curve that is kind of like this, comes and hugs the vertical axis, and then does that, which is, in the sense that we were discussing before, identical to the curve that you have for the isotherm of the liquid-gas coexistence. What do I mean? I could do the same type of collapse of data that I showed you before that I was doing for the coexistence curve. I can do that for these inverted coexistence curves. I can do the same collapse for this critical isotherm of the ferromagnet, and it would fall on top of the critical isotherm that I would have for neon, argon, krypton, anything else. So there is that kind of overall universality. Okay. Now, yes?
In this case, why didn't you draw the full loop of hysteresis?
Because I'm interested at this point with equilibrium phenomena. Hysteresis is a non-equilibrium thing. So depending on how rapidly you cool things or you not cool things, you will get larger curves. It's larger hysteresis curves.
So what would happen if we had high positive magnetic fields and we slowly go reduce it to zero and then go a little bit beyond and then just stay in that state for a long time? Will the
yes, if you wait sufficiently long time, which is the definition of equilibrium, you would follow the curve that I have drawn. There would be. So the size of the hysteresis loop will go down as the amount of time that you wait. Except that in order to see this, you may have to wait longer than the age of the universe. I don't know, but in principle, that's what's going to happen. All right. Yes.
When you create the flat line for temperature below the critical one,
Yes.
are you essentially doing sort of a Maxwell construction again, or is that too much even for this?
No. I mean, I haven't done any theoretical work. At this point, I'm just giving you observation.
Okay.
Once we start to give theory, there is a type of theory for the magnet that is the analog of Maxwell's construction that you would do for the case of the liquid gas. Indeed, you will have that as the first problem set, so you can figure it out for yourself. Anything else? Okay. So I kind of emphasized that functional forms are the things that are universal. And so in the context of the magnet, it is more clear how to characterize these functional forms. So one of the things that we have over here is that if I plot the true equilibrium magnetization as a function of temperature for fields that are zero, so H equals to 0. If I start along the zero field line, then all the way up to Tc, magnetization at high temperatures is of course 0. You are dealing with a paramagnet. By definition, it has no magnetization. When you go below Tc, you have a system that is spontaneously magnetized. Again, exactly what that means is it needs a little bit of clarification because it does depend on the direction of your field. The magnitude of it is well defined. If I go from H to minus H, the sign of it could potentially change, but the magnitude has a form such as this. It is, again, very similar, if you like, to half of that coexistence curve that we had for the liquid gas. And we look at the behavior that you have in this vicinity, And we find that it is well described by a power law. So we say that M as T goes to Tc for H equals to 0 is characterized or is proportional to Tc minus T to an exponent that is given the symbol beta. Okay? Now sometimes you can write this as Tc minus T to the, make it dimensionless. It doesn't matter, it's the same exponent. Sometimes in order not to have to write all of this thing again and again, we call this small t. It's just the reduced temperature from the critical point. And so basically what we have is that T to the beta characterizes the singularity of the coexistence line, the magnetization, all of that. Now, rather than sitting at H equals to 0, I could have sat exactly at T equals to Tc and vary H. So essentially, this is the curve. I sit at T equals to Tc. This is the blue curve. And we see that blue curve has this characteristic form, that it also comes to 0, not linearly. So there is an exponent that characterizes that again is typically written as 1 over delta. And so you can see that if I go back to the critical isotherm of the liquid gas system, for the liquid gas system, I would conclude that, say, delta V goes like delta P to the power of delta, or 1 goes with the other to the power of 1 over delta. So essentially, the shapes of these two things are very much related, characterized by these two exponents. What else? Another thing that we can certainly measure for a magnet is the susceptibility. So chi, let's measure it as a function of temperature, but for field equal to 0. Okay? So basically, I sit eventually at T equals to Tc, but I put on a small magnetic field and see how the magnetization changes. You can see that as long as I am above Tc in the paramagnetic phase, there is a linear relationship here. Chi is proportional to H, but the proportionality here is the susceptibility. As I get closer to Tc, that susceptibility diverges. Okay? So chi is proportional to T, diverges with an exponent that is indicated by gamma. Actually, let me be a little bit more precise. So what I have said is that if I plot the susceptibility as a function of temperature, at Tc it diverges. I could also calculate something similar to that below Tc. Below Tc, it is true that I already have some magnetization. But if I put on a magnetic field, the magnetization will go up. And I can define the slope of that as being the susceptibility below Tc. And again, as I approach Tc from below, that susceptibility also diverges. So there is a susceptibility that comes like this. So you would say, OK, there is a susceptibility above, and there is a susceptibility below, and maybe they diverge with different exponents. At this point, we don't know. Yes or no? We will show shortly that indeed the two gammas are really the same, and using one exponent is sufficient for that story. And the analog of susceptibility in the case of the liquid gas would be the compressibility. The compressibility is related somehow to the inverse of these PV curve slopes. We know that the sign of it has to be negative for stability, but right on the critical isotherm, we see that the slope goes to 0 for its inverse divergence. So there's, again, the same exponent gamma for some magnets also describes that divergence. Okay? Susceptibility is an example of a response function. You perturb the system and see how it responds. Another response function that we have seen is the heat capacity, where you put heat into the system, or you try to change the temperature and see how the heat is, energy is modified. And again, we experimentally observe, we already saw something like this when we were discussing the superfluid transition, the lambda transition, that the heat capacity as a function of temperature at some transition temperatures happens to diverge. And in principle, one can again look at the two sides of the transition and characterize them by divergences that are typically indicated by the exponent alpha. Again, we will see that there are reasons why there is really one exponent alpha. So this is essentially the only part where there is some zoology involved. You have to remember and learn where the different exponents come from. The rest of it, I hope, is very logical, but which one is alpha, which one is beta, which one is gamma? It's 4 things, 5 things you should remember. Okay? Now, the next thing that I want to do is to show you that the two things that we looked at about the liquid-gas transition, in fact, one of them implies the other. So we said that essentially by continuity, when I look at the shape of this critical isotherm, it should come down with this 0 slope. Or again, to continuously join the type of curve that I have for t greater than Tc of magnetization and t less than Tc below, I should have a curve that comes and hugs the axis or has infinite susceptibility. Now I will show you that the infinite susceptibility does in fact imply that you must have collective behavior. That is, this critical opalescence that we saw is inseparable from the fact that we have diverging susceptibility. I'll show that in the case of the magnet, but it also applies, of course, to the critical opalescence. So let's do a little bit of thermodynamics. So I can imagine that I have some kind of a Hamiltonian that describes my interactions among the spins in my iron or any other magnet that I have. And if I was to calculate a partition function, what I need to do would be to trace over all degrees of freedom of the system. Now, for the case of the magnet, it is more convenient, actually, to look at the ensemble that is corresponding to this. That is, fix the magnetic field and allow the magnetization to decide where it wants to be. So I really want to evaluate things in this ensemble, which really, to be precise, is not the Helmholtz ensemble, but the Gibbs ensemble. So this should be a Gibbs free energy. This should be a Gibbs partition function. But traditionally, most texts, including my notes, ignore that difference and log of this, rather than calling it G, we will call F. But that really doesn't make much difference. This clearly is a function of temperature and H. Now, if I wanted, and let's imagine that always we put the magnetic field in one direction, so I don't have to worry for the time being about the vectorial aspect. We will go back to the vectorial aspect later on. Clearly, actually, this is the net magnetization of the system. If I have a piece of iron, it would be the magnetization of the entire iron. And the average of that magnetization, given temperature and field, etc., I can obtain by taking a d log z by d beta h. Right? Because when I do that, I go that inside the trace, take a derivative with respect to beta h, and I have a trace of m e to the minus beta h plus beta hm, which is how the different probabilities are weighted, once because of the log z in the derivative I have a 1 over z to make these properly normalized probabilities. So that's the standard story that we know. Now, if I were to take another derivative, if I were to take a derivative of m with respect to h, which is what the susceptibility is after all. So the susceptibility of the system, it is the derivative of magnetization with respect to h. It is the same thing as beta derivative of m with respect to beta h, of course. So I have to go to this expression that I have on top and take another derivative with respect to beta h. The derivative can act on the beta h that is in the numerator, and what that does is it essentially brings down another factor of m, and the z is not touched. Or I leave the numerator as is and take a derivative of the denominator, and the derivative of z I have already taken. So essentially, because it's in the denominator, I will get a minus 1. The derivative of 1 over z will become 1 over z squared. It will also give me that factor that multiplies that factor itself. So I have e to the minus beta h plus beta hm. And this whole thing got squared. Okay? So a very famous formula, always true. Response functions such as susceptibilities are related to variances, in this case, variance of the net magnetization of the system. Of course, true for other responses. Okay, this doesn't seem to tell us very much. But then I note the following, that, okay, so I have my magnet. And what I have been asking is, what is the net magnetization of this piece of magnet and its response to adding a magnetic field? If I want to think more microscopically, if I want to go back in terms of what we saw for the liquid-gas system and the critical opalescence, where there were fluctuations in density all over the place, I expect that in reality also at some particular instance, when I look at this, there will be fluctuations in magnetization from one location of the sample to another location of the sample. It's kind of building gradually in the direction of the statistical field. I kind of expect to have these long wavelength fluctuations, and that's where I want to go. But at this stage, I cannot even worry about that. I can say that I define, in whatever way, some kind of a local magnetization, so that the net magnetization, let's say in d dimension, is the integrated version of the local magnetization. So magnetization density, I integrate it, I will get a net magnetization. Okay, I put that over here. I have two factors of big M, so I will get two factors of integration over r and r prime. Let's stick to 3 dimensions. Doesn't matter, we can generalize it to d dimensions. And here I will have m of r prime, and the average would give me the average of this m of r minus m of r prime, whereas in the second part, there are the product of two averages, m at r, average of m at r prime. So it is the covariance, right? So I basically have to look at the m at some point in my sample, the m at some other point r prime in the sample, calculate their covariance. Okay. Now, on average, this piece of iron doesn't know its left corner from its right corner. So just as in the case of the lattice, I expect once I do the averaging, on average, m of r prime should be only a function of r minus r prime. Right? So I expect that this covariance, that's indicated by mmc, is really only a function of the separation between the 2 points. Okay? Which means that one of these integrations I can immediately perform. There's the integral with respect to the relative coordinate and the center of mass coordinate. For getting boundary dependence, this will give me a factor of b. There was a factor of beta that I forgot. There is an overall beta. So I have chi beta. And then I have the integral over the relative coordinate of the correlations between 2 spins in the system as a function of separation. Okay? Now, of course, like any other quantity, susceptibility is proportional to how much material you have. It's an extensive quantity. So when I say that the susceptibility diverges, I really mean that the susceptibility per unit volume, the intensive part, is the thing that is diverging. But the susceptibility per unit volume is the result of doing an integration of this covariance as a function of position. Let's see what we expect this covariance to do. So as a function of separation, if I look at the covariance between 2 spins, okay, so there's this note that I have already subtracted out the average. So whether you are in the ferromagnetic phase or in the paramagnetic phase, the statement is how much is the fluctuation around the average at this point and this other point are related. Well, when the 2 points come together, what I'm looking at is some kind of a variance of the randomness. Okay? Now, when I go further and further away, I expect that eventually what this does as far as a fluctuation around the average is concerned does not influence what is going on very far away. So I expect that as a function of going further and further away, this is something that will eventually die off and go to 0. Let's imagine that there is some kind of a characteristic length scale below which the correlations have died off to 0. And I would say that this integral is less than or equal to essentially looking at the volume over which there are correlations. The correlations within this volume will typically be less than sigma squared, but let's bound it by sigma squared times the volume that we are dealing with, which is, I don't know, 4 pi over 3 c cubed. Coefficients here are not important. Okay? So if I know that my response function per unit volume, like my compressibility or susceptibility, if I know that the left-hand side as I go to TC is diverging and going to infinity, variance is bounded, I can't do anything with this. Beta is bounded, I can't do anything with this. The only thing that I conclude, the only knob I have is that C must go to infinity. So chi over v going to infinity implies and is implied by, in some sense, c going to infinity. Okay? So I was actually not quite truthful because you need to learn one other exponent. So how the correlation length diverges as a function of temperature is also important and is indicated by an exponent that is called nu. So C diverges as T to some exponent that is nu. So this is what you were seeing when I was showing you the critical opalescence. The size of these fluctuations became so large that you couldn't see through the sample. All kinds of wavelengths were taking place in the system. And if I had presented things elsewhere, I could have given you that as a prediction. I should have shown you, say, the critical isotherm looks like this. Therefore, if you look at it at TC, you shouldn't be able to see through it. This is really the proof. Okay? All right, so those are the phenomena that we would like to now explain. Phenomena being these critical exponent, alpha, beta, gamma, nu, etc., being universal and the same across very many different systems.
Question.
Yes?
Are there examples in elementary field, fundamental field theory, like, I mean, like in the standard model or in quantum field theory, where something like this happens, where there's, I mean, it's not a thermodynamical system, it's like elementary theory, and yet.
Yeah. In some sense, the masses of the different particles are like correlation lengths, because it is the mass of the particles, like in the Yukawa potential, that describes the range of the interactions. So there are phenomena, such as the case of phonons or whatever, where the range is infinite. So in some sense, those phenomena are sitting at the critical point. Okay. So the name of the statistical field theory that we will construct is Landau-Ginzburg, and originally constructed by Landau in connection to superfluidity. But it can describe a lot of different phase transitions. Let's roughly introduce it in the context of these magnetic systems. So basically, I have my magnet, and again, in principle, I have all kinds of complicated degrees of freedom, which are the spins that have quantum mechanical interactions, the exchange interactions, whatever the result of the behavior of electrons and their interactions with the ions is, that eventually something like nickel becomes a ferromagnet at low temperatures. Now, hopefully, and actually precisely in the context that we are dealing with, I don't need to know any of all of those details. I will just focus on the phenomena that there is a system that undergoes a transition between ferromagnetic and paramagnetic behavior, and focus on calculating an appropriate partition function for the degrees of freedom that change their behavior on going through TC. Okay? So what I expect is that, again, just like we saw for the case of liquid gas system, on one side for the magnet, there will be on average zero magnetization in the paramagnet, but there will be fluctuations of magnetization, presumably with long wavelengths. On the other side, there will be these fluctuations on top of some average magnetization that has formed in the system. And if I stick sufficiently close to TC, I expect that that magnetization is small. That's where the exponent beta comes from. So if I go sufficiently close to TC, these m's that I have at each location hopefully will not be very big. So maybe in the same sense that when I was doing elasticity by going to low temperatures, I could look at small deformations. By sticking in the vicinity of TC, I can look at small magnetization fluctuations. So what I want to do is to imagine that within my system that has lots and lots of electrons and other microscopic degrees of freedom, I can focus on regions that I average, and with each region that I average, I associate a magnetization as a function of position, which is a statistical field in the same sense that the displacement was. See, over here, I will write this quantity, the analog of the U, in fact, by using two different vectorial symbols for reasons that will become obvious shortly, hopefully. Because I would like to have the possibility of having R to describe systems that live in D dimensions, where D would be 1 when I'm dealing with a wire, D would be 2 if I'm dealing with a flat plane, D equals to 3 in 3-dimensional space. Maybe there is some relationship to relativistic field theories where D would be 4 for space-time. But M, I will allow to be something else that has components M1, M2 to Mn. And we've already seen two cases where n is either 1 or 3. Clearly, if I'm thinking about the case of a ferromagnet, then there are 3 components of the magnetization. N has to be 3. But then if I'm looking at the analogous thing for the liquid-gas system, the thing that distinguishes different locations is the density fluctuations, and that's a scalar quantity. So that corresponds to n equals to 1. Turns out that when we are dealing with superfluidity, where what we are dealing with is a quantum mechanical object that has a phase and an amplitude, it has an x component, real and imaginary component, that corresponds to n equals to 2. Again, n equals to 1 would describe something like liquid gas. N equals to 3 would correspond to something like a real magnet. And there is actually no relationship between n and d. N could be larger than 3. So imagine that you take a wire. So x is clearly 1-dimensional, but along the wire you put 3 component spins. So n could still be 3. Right? So we can discuss a whole bunch of different quantities at the same time by generalizing our picture of a magnet to have n components and exist in d dimensions. Okay? Now the thing that I would like to construct is that I look at my system and I characterize it by different configurations of this field, M of R. And if I have many examples of the same system at the same temperature, I will have different realizations of this statistical field. I can assign the different realizations some kind of a weight or a probability, if you like. And what I would like to do is to have an idea of what the weight or probability of different configurations is. Just because I have a background in statistical mechanics in statistical mechanics, we are used to Boltzmann weights, so we take the log of weights or probabilities and call them some kind of effective Hamiltonian. And this effective Hamiltonian is distinct from the true microscopic Hamiltonian that describes the system. And it's just a way of describing what the logarithm of the probability for the different configurations is. And so say, well, okay, how do you go and construct this? Well, I say, okay, presumably there is really some true microscopic Hamiltonian, and I can take whatever that microscopic Hamiltonian is that has all of my degrees of freedom, and then for a particular configuration, I know what the probability of a true microscopic configuration is. Presumably what I did was to obtain my M of R by somehow averaging over these other true degrees of freedom. So the construction to go from the true microscopic probabilities to this effective weight is just a change of variable. I have to specify some configuration M of R in my system. That configuration of M of R would be consistent with a huge number of microscopic configurations. I know what the weight of each one of those microscopic configurations is. I sum over all of them, and I have this. Now, of course, if I could do that, I would immediately solve the full problem and would need to have to deal with this. Clearly, I can't do that, but I can guess what the eventual form of this is in the same way that I guessed what the form of the statistical field theory for elasticity was, just by looking at symmetries and things like that. Okay? So, in principle, W from change of variables starting from e to the minus beta h. In practice, from symmetries. And a variety of other statements and constraints that I will tell you about. Actually, let's keep this. And let's eliminate this. Okay. So there is beta h, which is a functional of m as a function of this vector x. Okay. First thing that I will do is what I did for the case of elasticity, which is to write the answer as an integral in d dimensions of some kind of a density at location x. So this is the same locality type of constraint that we were discussing before, and has some caveats associated with that. This is going to be a function of the variable at that location x. So that's the field. But I will also allow various derivatives to appear so that I go beyond just single point, which would just give me independent things happening at each location, by allowing some kind of connections in a neighborhood. And if I go and include higher and higher order derivatives, naturally I would have more terms. Somebody was asking me, you were asking me last time, in principle, if the system is something that varies from one position to another position, the very function itself would depend on x. But if we assume that the system is uniform, then we can drop that also. Okay? So to be precise, let's do this for the case of zero field. Because when you are at zero field in a magnet, the different directions of space are all the same to you. There is no reason to be pointing one direction as opposed to another direction. So because of this symmetry in rotations, in this function, you cannot have m. Actually, you couldn't have m for other reasons. Well, okay, you couldn't have m because it would break the directionality. But you could have something that is m squared. Again, to be precise, m squared is some, let's say, alpha running from 1 to n, m alpha of x, m alpha of x. Now, if the different directions in space are the same, then I can't have a gradient appearing by itself because it would pick a particular direction. In the same sense that m squared, two m's had to be appearing together, if the different directions in space, forward and backward, are to be treated the same, I have to have gradients appearing together in powers of 2. So there is a term that, before going that, let's say also, sometimes I will write something that is m to the fourth. M to the fourth is really this quantity m dot m squared. If I write m to the sixth, it is m dot m cubed, and so forth. So there's all kinds of terms such as that can be appear in this series. Gradients, there is a term that I will write symbolically as gradient of m squared. And by that I mean you take a derivative of m alpha with respect to the ith component, and then repeat the same thing, sum over both alpha and I. So that would be a gradient. So basically, the xi appears twice, m alpha appears twice. And you can go and construct higher and higher order terms and derivatives, again ensuring that each index, both on the side of the positions x and in the side of the fields m, is a repeated index to respect the symmetries that are involved. Okay? So if there is actually maybe one other thing to think about, which is that, again, like before, I assume that I can make an analytical expansion in M, right? And who says you are allowed to do an analytical expansion in M? Again, the key to that is the averaging that we had to do in the process. And I want you to think back to the central limit theorem. Let's imagine that there is a variable x where the probability of selecting that variable x is actually kind of singular. Maybe it is something like e to the minus x that has a discontinuity. Maybe it even has an integrable divergence at some point. Maybe it has additional delta function, all kinds of things. It's a very complicated, singular type of a function. Now I tell you, add thousands of these variables together and tell me what the distribution of the sum is. And the distribution of the sum, because of the central limit theorem, has to look Gaussian. So when you take its log, it has a nice analytical expansion. So the point is that, again, part of the coarse graining that we did to get from whatever microscopic degrees of freedom that we had to reaching the level of this effective field theory, we added many variables together. And because of the central limit theorem, I have a lot of confidence that quite generically I can make an analytical expansion, such as that's what I have done. So having done all of this, you would say that in order to describe this magnet, what we need is to evaluate a partition function, let's say, as a function of temperature, which if I had enormous power, I would do by trace of e to the beta h microscopic. But what I have done is I have subdivided different configurations of microscopic degrees of freedom to different configurations of this effective magnetization. And so essentially that sum is the same as integrating over all configurations of this constrained magnetization field. And the probabilities of these configurations of the magnetization field are exponential of this minus beta h that I'm constructing on the basis of principles that I told you. Principles where that I first of all have a locality, I have an integral dt of x, and then I have to write terms that are consistent with the symmetry. First term that we saw is consistent with the symmetry is this m squared. Let's give a name to its coefficient, just like the coefficient of elasticity. I put a mu over 2. Let's put here a t over 2. There will be higher order terms. There will be m to the 4th. There will be m to the 6th. There will be a whole bunch of things in principle. There will be gradient types of terms. So there will be k over 2 gradient of m squared. There will be L over 2 Laplacian of m squared. There would be higher order terms that involve multiplying m's and various gradients of m, etc. And actually, in principle, there could be an overall constant. So there could be up here some overall constant of integration. Let's call it beta f0. Which depends on temperature and so forth, but has nothing to do with the ordering of these magnetization type of degrees of freedom. Actually, if I imagine that I go slightly away from the h equals to 0 axis, just I did before, I will add here a term minus beta h dot m and evaluate this whole thing. So this is the Landau-Ginzburg theory. In principle, you have to put a lot of terms in the series. Our task would be to show you quite rigorously that just a few terms in the series are enough, just as in the case of theory of vibration for small enough vibration. In this case, the analog of small enough vibration is to be close enough to the critical point, exactly where we want to calculate these universal exponents. And to then calculate the universal exponents, which will turn out to be a hard problem that we will struggle with in the next many lectures.